Okay, thanks for the introduction, and also thank you for the invitation. I'm really glad to be here and have the opportunity to talk about our work with around FRI-based SNARKs. So this is joint work with the researchers that appear here. And let's begin with defining terms. So what is a FRI-based SNARK? So it's a kind of a loose term that, for the purposes of this talk, I will use to have the following meaning. So a FRI-based SNARK will be a SNARK that is built following the following recipe, which is you take a PIOP, Polynomial Interactive Oracle Proof, you compile it with FRI and Merkle trees, and then you do the Fiat-Shamir transform. So if your SNARK is built in this way, then we call it FRI-based SNARK. So just to set up some notation and terminology, let's review what's a PIOP. In a PIOP, it's an interactive protocol. There's a prover and verifier. There's a problem statement and a witness. The witness is only known to the prover. And then the prover and the verifier exchange messages for a certain number of rounds. And and then the verifier takes, so the particularity of a PIOP is that the messages that the prover sends are polynomials of low degree. So the prover sends polynomials of low degree, and at the end of this interactive phase, the verifier opens these polynomials at random points, and then based on whether or not these openings satisfy some algebraic relations, it accepts or rejects the proof. Okay, a key point in PIOPs when one analyzes the security of PIOPs is that you assume that the maps that the prover sends are polynomials. And this is a key assumption. So you assume this, and then you prove that the PIOP is secure under this assumption. And this is actually a very strong assumption, which makes the security analysis of PIOPs relatively easy, I would say. Usually, if you've worked with PIOPs or read some papers on them, you usually end up finding a statement of this form. So you start analyzing the security of PIOP, and you end up proving that unless the verifier is very unlucky and sends a root to some low-degree polynomial, then the attacker cannot break the protocol, for sure. And then you use the Schwarzschild lemma, which says that the greedy polynomials have a few number of roots, and you get that the attacker can break the protocol only with negligible probability. So the degree of the polynomial, the maximum number of roots it can have, over the size of the challenges the verifier can send. So analyzing the security of PIOPs is relatively easy because they rely on this very strong assumption, the assumption that the prover sends polynomials. So this is very nice. Analyzing PIOPs is like the PIOP is a very nice abstract framework that facilitates reasoning about zero-knowledge proofs. But in practice, PIOPs are not usable because there's several issues with them. First of all, how does the verifier check that the maps it receives are low-degree polynomials? Like, one thing it could do is to check all the evaluations of the maps and see if they are consistent with being a polynomial. But this would make the verifier extremely slow. Another issue is that the maps are too large to be sent. So you cannot just have the prover send the maps, and because this would make the proof size huge, and it would be very similar to the prover just sending the witness altogether. So the typical solution to these issues are to compile the PIOP with a polynomial commitment scheme, in which you take the PIOP, take a polynomial commitment scheme, and replace the messages that the prover sends by commitments to the polynomials. So now the prover, instead of sending polynomials, sends commitments. And recall that at the end of the interactive phase, the verifier opens the polynomials at some random points. Now the verifier has commitments, so it cannot just open the commitments. So it interacts, when it wants to open one of the maps, it interacts with the prover according to the specification of the PCS and opens the polynomials at the points it wants to open them. So examples of PCSs are the KZG1, the inner product argument-based PCSs, and FRI-based polynomial commitment schemes. Though we will talk more about FRI-based polynomial commitment schemes because in the literature, well, not in the literature, but practitioners often use them as if they were PCSs, but they are not actually PCSs unless you configure them in a very restrictive way, which makes FRI quite slow. So in practice, the way FRI is configured makes FRI not be a PCS. And we will come back to this later. And it's one of the key points that we address in this work. So you have the PIOP, you have the commitment scheme, and now there's a theorem that says that if the PIOP is secure and the polynomial commitment scheme is secure, then the new protocol is secure. So you can design your PIOP, prove that it is secure. That's easy, relatively easy, as I argued before. Take a PCS, which is from the literature, which is already proven secure. You compile it, and you get a secure protocol. So if you follow this recipe, you get it's kind of easy. You get a secure, succinct argument just by looking at the PIOP. Okay, and so in a FRI-based SNARK, we take a PIOP, compile it with FRI and Merkle trees. Let's pretend that FRI and Merkle trees make a PCS, which do not, but let's pretend it is. And then we apply the Fiat-Shamir transformation. And in the interest of time, I will not go over the Fiat-Shamir transformation. Probably everybody here knows how it works. The idea is that you replace the challenges the verifier would send by hashes of all the messages exchanged before. And if you model the hash as a random oracle, then it's as if the prover is simulating the verifier. Okay, yeah. So I'll just mention some examples of FRI-based SNARKs. The most well-known example is STARK, the STARK protocol from Starkware. And then there's a flurry of other protocols now that can be seen as FRI-based SNARKs. For example, Plonky2, which is, you could say it's Plonk, but changing the FRI protocol, changing the KZG commitment scheme by FRI. And Plonky2, RIS0, Bujum are kind of similar protocols that do this. Okay, so there's this recipe, and our work analyzes two potential pitfalls. One is around the Fiat-Shamir transformation of protocols, and the other is, as I mentioned, the issue that FRI is not really a PCS, a commitment scheme. So let's discuss Fiat-Shamir. So in general, you can have an interactive protocol, and then you can consider the Fiat-Shamir transform of the protocol, and get a protocol that is not secure. So you can have a very secure interactive protocol, Fiat-Shamir transform it, and get a disaster as a result. There is a well-known example, which is the sequential repetition of a smaller protocol. You take a protocol with soundness error 1/2, repeat it t times, and the interactive version of this repetition has a soundness error 1/2 to the t. However, if you do the Fiat-Shamir transform of this new protocol, it's a disaster. Like, the security is basically 1/2. Very roughly speaking. You almost gain nothing from sequential repetition. There's another example which is less well known and actually was described very recently, last year, which is the parallel repetition of a smaller protocol. And I will focus on this example because it's less well known. So what do I mean by parallel repetition? Let's assume we have a small protocol, Pi0, which has 64 bits of security or 32 bits of security. And we want to increase its security by repeating it in parallel. So we create a new protocol where now the prover, instead of sending one message as its first message, it sends two messages. And the verifier replies with two challenges, and so on. So it's just like executing Pi0, but with two threads in parallel. And the verifier accepts the proof, this proof, even only if the verifier in Pi0 would accept each of the columns as a valid proof for Pi0. So this is the 2x parallel repetition of Pi0, which I denote Pi and this Cartesian product. So now I'll explain why, if you consider the interactive protocol obtained in this way, the security is quadratically larger than the security of pi 0. If the soundness error of pi 0 is epsilon, the soundness error of this one is epsilon square. But now I'll argue that when you do the Fiat-Shamir transform, the soundness error is epsilon, pretty much, 2 times epsilon. So how can an attacker attack this parallelly repeated protocol? So here there's V, but there should be a prover, because now we are in the Fiat-Shamir setting. Okay, so this V is just computing the hash of previous messages. So the attacker proceeds as follows. It chooses any 2 messages, first messages, M1 and M1 prime, and it computes the challenges by hashing the previous messages. And now comes the key point, which is it checks if the first component of the challenge is a special challenge that would allow the prover in the small protocol to break the protocol. So to make this more concrete, if you've worked with PIOPs, for example, you've probably seen that if the verifier sends you a root to certain polynomial, then the prover can break the protocol. Like that's typical situation that you don't want you make sure that the verifier can that it is very hard for the verifier to send you a root, because if you make sure of that, then it cannot break the protocol. So imagine that this C1 is a root to this type of polynomial. So if this C1, the first component, is a root, it means that if prover was only executing pi 0, it could break pi 0. So the prover computes the challenges and tries to sees if this C1 is special. If it is, then it moves to the next phase, to the next slide. Otherwise, it repeats and goes back to step 1. Chooses a new message, gets new challenge, and checks again if the new challenge is the first component is special. And in expectation, it needs basically 2 to the lambda iterations to succeed, where lambda is the security parameter of the interactive protocol. That's a very rough and loose statement, but just to simplify things, basically what the prover is doing here is breaking pi 0. And if epsilon is the security of pi 0, well, it needs to make at least this amount of repetitions to, in expectation, make sure that it gets one of these roots. Okay, so let's suppose that the prover has managed to get this special first challenge. How does it proceed? Well, now the first thread is basically broken. The prover knows how to complete the first thread and get a valid proof for pi 0. What does it do next? For the first thread, it will choose messages in a way that it allows it to break this thread of pi 0. And it chooses M2 prime arbitrarily. It proceeds like as before. It computes the new challenges. And again, it checks if the second component now of the new challenges is a special challenge that allows it to break pi 0. So again, for example, it checks if C2 prime is a root to some polynomial that allows it, that would mean that the prover breaks the protocol pi 0. If it gets this special challenge, it is happy. Otherwise, it goes back to this step, chooses a new M2 prime, gets new challenges, and so on. So again, it needs about 2 to the lambda iterations, where lambda is the bits of security of the small protocol. And what happens if it succeeds in the 2 steps? It gets one column, which contains a valid proof for pi 0, and another column which contains a valid proof for pi 0. So the verifier accepts. If the prover succeeds in these 2 steps, the verifier accepts. Yeah, and we saw that succeeding at step 1 requires 2 to the lambda work, and succeeding at step 2 requires 2 to the lambda work. So in general, the prover needs to make 2 times 2 to the lambda work. So 2 to the lambda plus 1 work. So in a sense, the security has only increased by 1 bit, but we were expecting it to increase by 2 times. because the interactive version of the parallel repetition has this soundness. So using the parallel repetition has done nothing, basically. Like you repeated the protocol in parallel, applied the Fiat-Shamir transform, and didn't gain any security, essentially. And I'll skip this for the interest of time. So, okay, we just saw that you can have a super secure interactive protocol, apply the Fiat-Shamir transform, and get a disaster. So this raises the question, when can we be sure that if we apply the Fiat-Shamir transform, we get something that's as secure as the initial protocol? And the answer, for example, you can do several things, but one of the things you can do is prove that your initial protocol, the interactive one, satisfies some strong notion of security. There's several to choose from, but the typical one is special soundness. If you prove that your protocol is special sound, which I'm not going to define now, then the Fiat-Shamir transform of the protocol is, roughly speaking, as secure as the initial protocol. And you can also prove that you can choose a different type of security notion, of strong security notion, for example, round-by-round knowledge soundness or round-by-round soundness. If you prove that your protocol satisfies this notion, then the resulting Fiat-Shamir transform protocol is roughly as secure as the initial protocol. And just to give since round-by-round soundness is a bit less known than special soundness, I'll try to give an intuitive idea of what it is without getting into the formal definition. So in the example of parallel repetition and sequential repetition, you could say, intuitively speaking, that the overall soundness of the big protocol is the accumulation of smaller checks made during this big protocol. So it's like you are making several checks, and the final soundness in the interactive version is the conjunction of all this soundness. But this is precisely what the attacker in the Fiat-Shamir transform can exploit. It can rewind proofs and try to break these small soundness checks, these checks that have small soundness. And then the Fiat-Shamir transform doesn't work as expected. So that's the issue with these examples I gave. And round-by-round knowledge soundness is a notion that tries to state that this doesn't happen. So the formalization is different than what I'm just saying, but this is the intuition of what round-by-round knowledge soundness says. Basically that the security of the protocol is not the accumulation of several checks that are not very secure. So basically to prove that your protocol is round-by-round sound or knowledge sound, you have to end up showing that every check you make has the soundness error that you are targeting. Like if you are targeting 128 bits, all checks should have 128 bits. And if you are wondering what's the relation between special soundness and round-by-round soundness, in a recent paper we put on preprint, we prove these relations. So round-by-round knowledge soundness is the strongest. It implies special soundness, which in turn implies round-by-round soundness. And we also showed that special soundness does not imply round-by-round knowledge soundness, so it's strictly more strong. Okay, so now let's discuss FRI. So just to set things up, in FRI the prover has a function in a field, and the verifier can access the values of the function in some subset of the field. And the goal of the prover is to convince the verifier that f, the function, is a polynomial of low degree. Well, that's what we would like. That would be the ideal world, but unfortunately, FRI is a bit more complicated, and it only allows the prover to convince the verifier that fx behaves similar to a polynomial of low degree, but not that it is a polynomial of low degree. And what does similar mean? It means it's captured by the definition of delta closeness, which means that fx is delta close to a polynomial if it agrees with it on a relatively large subset of this domain. And here you have the math behind it. It's not important for our purposes. So one of our results is that the FRI protocol is round-by-round knowledge sound. This also implies that it is spatial sound by the previous result I mentioned, because round-by-round knowledge soundness implies spatial soundness. This was proved concurrently by STARKware. They published it pretty much at the same time as we put it online. And in particular, it means that you can use FRI safely with the Fiat-Shamir transform. Okay, and about using FRI as a polynomial commitment scheme. So I mentioned at the beginning of the talk that this is a problem, and I'll try to explain why now. When close, so recall that FRI proves that a map is close to a low-degree polynomial. When close is very close, then FRI, you can prove that you can use it as a PCS, a polynomial commitment scheme. And the way you do it is you use the typical KZG-like check. If you want to open a map that has been committed, you use FRI to check that this quotient is a low-degree polynomial. This is kind of a standard thing in KZG, and you also do this in FRI. Here, very close, just to be clear, it means that the proximity parameter is within the so-called unique decoding radius. However, this choosing delta in this form leads to an inefficient FRI protocol that is not used in practice. So in practice, you never choose this proximity parameter to be so low. And all protocols I mentioned before, for example, STARK, Plonky2, RISC-0, they use a larger proximity parameter that goes up to the so-called Johnson bound. And when you take this large proximity parameter, then this protocol in here is no longer a polynomial commitment scheme. And the reason is that you can have multiple polynomials that are delta close to your map. And this allows the prover to open any of these polynomials. So when you query the commitment, the prover can choose between a certain list of polynomials and give you that evaluation. So the prover is not really committing to a polynomial anymore, it's committing to a list of polynomials, and this is a problem. This was studied, for example, in the Redshift work on the context of using FRI on Plonk. However, if you take the Redshift approach, you get an issue, which is that the soundness error scales exponentially on the width of the trace. And for example, Plonky2, I think, uses traces of with more than 100. So you cannot just use Redshift to prove that Plonky2 is secure, for example, because you would get, like, the result you get is soundness error of 2 to the 100, which is not what you want. And yeah, and also STARK-type protocols use FRI. So they compile PIOPs with FRI, but they don't treat the FRI as a PCS. And there are several papers by STARKware on this topic. Recently, Ulrich Habok published a summary or survey on the FRI protocol, and he improved a little bit the soundness estimates that appear in deep FRI and in STARK and all this work. So here is our main result. The main result of the talk is the following. We describe a large class of PIOPs with the following property. So if you take a PIOP in this class and you prove that it is round-by-round knowledge sound or round-by-round sound, then the FRI-based SNARK that you obtain from it is sound or is knowledge sound. So it's a SNARK with K. And by FRI-based SNARK, I mean you take the PIOP, use FRI and Merkle trees, and then the Fiat-Shamir transform. So the key point, the nice thing of this result is that it gives a wide class of PIOPs where to analyze the security of the final SNARK, you don't need to leave the PIOP setting. You can just prove that the PIOP is round-by-round sound or knowledge sound, which, as I argued at the beginning of the talk, it's relatively easy. And for example, an application of this strategy is we show that ethSTARK and Plonky2, as in the PIOP forms, are a round-by-round knowledge sound, and that they are in this class, the class of the theorem. And a corollary then is that these protocols are knowledge sound, and they have the knowledge sound that we expected them to have. And for ethSTARK in particular, this was also proved by Starkware concurrently. And that's the end of the talk. Thank you.
Questions? It was that clear? Oh, there we go. I guess I can reach over to you.
Thanks for the talk. So in that diagram where you connected two parallel protocols, do they necessarily have to be the same, or could it be two different protocols but just applied independently?
They can be two, yeah, different protocols for sure.
Okay.
Yeah, the same attack applies.
Do you know if that has like bigger implications for, I guess, other protocols that we use today? I guess, yeah, the knowledge soundness and or round by round says something about whether the protocol could be decomposed into those like independent chunks or independent provers.
Yes, but if you take the parallel repetition of a protocol or two protocols repeated in parallel and you try to prove that it is round by round sound, you will get a bad soundness error. You will get the soundness error of the less secure protocol, and that's it. You won't gain anything.
Okay, so that already captures that, like that the round-by-round sound protocol can't be split into those independent parts.
Yeah.
Okay.
Yeah,
cool.
yeah.
We have a question over there? Did we have a question in the back? No.
Oh, sorry, no.
No. Any other questions? No? Thank you very much, Albert.
Thanks.